In this example, we have a 20-pound sign that is being hung by two cords in the ceiling, labeled as T1 and T2, as shown in the diagram. If the angle formed by T1 in the ceiling is 45 degrees, so that means this is 45 degrees here, and the angle formed by T2 in the ceiling is 38 degrees, right here, we are going to find the tension in pounds of each cord. Notice that these two tension cables are themselves hanging up something that is itself in pounds, this sign being in 20 pounds. So that means the tensions that we find will also be in that same unit, as the magnitudes should be in the same unit measure. Now, this question can be done in a variety of ways. The traditional way is to write T1 and T2 as two vectors in component form. You can find the component form by considering the polar component form of the magnitude times cosine and sine of the direction angle. That should have already been demonstrated in a previous example in the previous lesson. In this case, though, I'm going to demonstrate the other way that we can solve this problem that takes a little bit less time. Note, however, I want to say up front that this demonstration and this method will only work with examples like this that can be structured in a two-dimensional diagram. This will not work for anything that is in a three-dimensional space. So if you have vectors in three-dimensional space. However, in this class, we only talk about two-dimensional vectors, so we can work with this method. What the method interprets, or what the method takes in, is considering the two tension cables as vectors and rewriting this situation and redrawing it as an addition of vectors. So here, really, we have our two tension cables. I have T1 as its own vector, a vector that is being pulled up toward the ceiling, and T2 as another vector. We're trying to find the tension that these two tension cables have in pounds. And keep in mind that these two tension cables are themselves holding up this sign of 20 pounds. If the sign were in free fall, or if it was falling down, it was not static, then that means that the amounts of tension these two cables have is not sufficient to hold up the 20-pound sign. But because it is, what that means is that the resultant of these two tension cables, the resultant of this should be sufficient to hold up 20 pounds upward towards the ceiling. Note that I have 20 pounds represented as moving upward because in this case these tension cables are holding the sign up. It is preventing the sign from falling anymore. The reason I draw it like this is because when we have vectors and we're trying to combine them, specifically T1 and T2 together, combined should total up to an amount of 20 pounds of tension being pulled vertically upward. We can redraw that then when we consider how we can add vectors geometrically. For example, I can draw the vector T1 just as it is, and then from the terminal point of T1, I can then draw T2. T2 from the terminal point of T1 is going up and to the right, so I'm going to draw my vector for T2 accordingly. And the resultant of these two vectors, when you add them together, should correspond to 20 pounds of weight being held up. And from here, we have a triangle that we can use. And if we can evaluate the values within this triangle, we can then calculate the tension cables using other trigonometric methods. So let's do that. From the angle measures we are told, we have for tension cable 1, it has a 45-degree measure with the ceiling, which we have represented as a horizontal line. That means if I draw a horizontal line with T1, I will do that both at the terminal point for T1 and at the initial point for T1. Then we know the angle measure from the horizontal to the diagonal of T1 should be 45 degrees. So that means this is 45 degrees, and this is also 45 degrees. Because of that, and that this is creating a right angle measure here with the horizontal and the vertical, we have therefore that the angle measure inside this triangle is 45 degrees. So we now have one other value to represent this triangle with. I can do the same thing with T2. We are told that T2 has an angle measure of 38 degrees with the ceiling, which is another horizontal line. So if I draw a horizontal line at both the initial point of T2, which we already have, as well as the terminal point of T2, I can say that the angle measure from or between the horizontal line and the diagonal line for T2 should be 38 degrees, meaning that this angle measure here is 38 degrees, as well as from the horizontal to the T2 vector here is 38 degrees. So, because this creates another right angle measure up at the top of this triangle, I therefore should be able to find the angle measure inside the triangle there as the complement of 38 degrees, which that would be 52 degrees. This is getting a little bit busy, so I'm going to redraw this triangle just to clean up what we've already solved here. T1, T2, we now know that this is 45 degrees, and we know this is 52 degrees. And we also know that this side is representing 20 pounds of weight. Now, that's not all we know, because since we have two angle measures inside a triangle, we should also be able to evaluate the third. We can either do that by considering it as the supplement of the other two angle measures combined together, or we can consider it as the addition of 38 and 45 degrees, as represented by this second triangle I drew, or the second diagram I drew. 38 plus 45, or the supplement of 52 and 45, which I'll write down here. 180 minus 52 degrees minus 45 degrees. That should give you 83 degrees. So that's our angle measure inside this triangle. And now we know more than enough. We have all three angle measures in this triangle, this other representation of the addition of vectors, and we know one of the side lengths. So we should have enough information using the law of sines in order to find the magnitude of T1 and the magnitude of T2. Let's start by evaluating the magnitude of T1 using the law of sines. The magnitude of T1, we can set that to be divided by sine of the angle measure across from T1, which is 52 degrees here in the triangle. So that's sine of 52 degrees. And I can set that fraction or ratio equal to a magnitude we do know of 20 pounds divided by sine of the angle measure across from 20 pounds, which is 83 degrees in that triangle there. So that's sine of 83 degrees. We can solve for the magnitude of T1 then by just multiplying sine of 52 over to get 20 sine of 52 degrees divided by sine of 83 degrees. And we can approximate that solution. Let's use a calculator for that purpose. Do make sure that you're in degree mode, since we will be plugging in degree measures into sine here. 20 sine of 52 degrees divided by sine of 83. That gives us overall 15.88, or to one decimal place, 15.9. So that's the amount of pounds the first tension cable T1 is holding. And we can solve for T2 using the same method. In this case, though, the magnitude of T2 will be set to be across from the angle measure of 45 degrees. So that'll be sine of 45 degrees this time. And I will set that equal to the exact same ratio I used in the previous question, or the previous evaluation. Therefore, then, the magnitude of T2 will be 20 times sine of 45 degrees instead, divided by sine of 83. Just like the previous one, we can evaluate that with a calculator here. 20 sine of 45, do make sure you're in degree mode, divided by sine of 83. And that gives you 14.2 to 1 decimal place. So 14.2 pounds as our solution. Those would be our two solutions. Now, one thing I will say at the end of this problem. It is a common misconception that the two tension cables together should add up to exactly 20 pounds of force being pulled vertically. If that were the case, then those two tension cables should be going in the same direction as the amount of weight that is being held. The weight is being held vertically up, but these two tension cables are going diagonally. When you have these two tension cables pulling away slightly with the sine, then they together are compensating to be more than the 20 pounds of weight, but individually they will be less than 20 pounds. This is basically, you can think about if you are holding up a heavy object by yourself, then you are holding it up with all the amount of force necessary to hold that object. But if you and a friend are together holding up an object with your hands, then you are splitting the weight. However, you are not splitting the weight equally. You are splitting the weight based on the angle of the force that you are using to hold up that object.